My name is Chen, and I'm presenting my project, which is the design and application of electrical field in the construction of the polydimethyl siloxane in the study of dynamic tactile interfaces. Basically, I'm working under a larger project called Study of Dynamic Tactile Interface by Agatha Cadet and Dr. Kretschmar. And the goal of Cadet's project is to develop dynamic tactile interfaces that will enable visually impaired and blind people to access visual information. So what does that mean? That basically means we're creating a material that you can place on top of a touchscreen that will create bumps when we add electrical charge to it, and it'll allow blind people to feel the screen. So for example, if you're at an ATM and you're trying to take out money, but you're blind or visually impaired, you can activate that feature and then you can feel your way around the screen. So it's like a, I guess a touch feature of it. So narrowing down, my goal in the Cadet's project is to design and create a device and a method that can apply electrical field to a PDMS compound during the curing stage. So PDMS is pretty much the material we're using, but then we need to apply electrical charge to it so it forms a better pattern. What is polydimethyl siloxane, which is PDMS for short. It's actually a silicon-based organic polymer, and it's known for unusual flow properties. So before curing, it acts like a viscous liquid, similar to honey, so it flows pretty well. It's almost like a very soft liquid, but then after curing, it acts as an elastic solid, so it's pretty much similar to rubber or something that's elastic. And this material can be found in several applications that include contact lenses, medical devices, shampoos, caulking and lubricating oils, heat-resistant towels, and there's so much more examples. It can be really applicable. So the procedure for creating PDMS, we have to create a mixture of base and curing agent. And this mixture should be containing the curing agent that's 10% of the base's mass. Then we pour approximately 1 gram into a Teflon mask folding block. I'll show you the pictures in the next few slides. And we can clean this block with nitrogen first. Then we place it in the desiccator container setup under vacuum to remove air bubbles. The desiccator container setup is basically like a clear container that's airtight, and we can apply a vacuum pump to it to suck out the air. And we will leave it inside for 30 minutes, but then after 5 minutes, we will remove it from the vacuum first to prevent bubble buildup, and then we move back to the vacuum again. After this process of desiccating the oxygen and the bubble buildup, then we put it in an oven overnight at 70 degrees Celsius. Okay. So, safety concerns with PDMS is you always have to wear gloves, because if you get on your fingerprints, it can get into the gap between your fingerprints, and that can be pretty uncomfortable. And likewise, you don't want to get into your eyes either, so you gotta wear goggles. So the purpose of the electrical field setup is to add a charge to it, and then it will align it in a better formation and pattern. So in this case, where you have an example of the PDMS particles, they're not electrically charged, so they tend to be scattered, and you have gaps here, 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 but they're somewhat clustered here, so it's very disorganized and inconsistent. So we want to achieve something that looks more pattern like this. Is actually a model made out of ping pong balls, and if you add an electrical charge to it, it'll form polar ends on each particle, and it'll pretty much behave like a magnetic material and form this pattern that's more uniform and more consistent. So the initial design ideas include using sheets of aluminum foil, which we have here. We cut strips of aluminum foil, and we want to use a thin electrical plates between the PDMS while it's curing, so we can add electrical charge to it. And one of the earlier potential problems that we saw was that it could include shortages, because the PDMS material that we're using is going to be actually, we're trying to create a very thin slice of it. So that means the electrical plates will be very close to each other, and it can create shortages. So we did 5 tests, and these are the ratios and of the bases and curing agents that we used. First test was pretty much a test that I created under supervision of my mentor. Second one, I created without supervision. Third one, we used secure electrical plates. Fourth one, secured and airtight electrical plates. And fifth one was a method that I came up with, and my mentor tried it out. So the first and second test were created under supervision. The first test was created under supervision, and the second was created without supervision. So this was the first one that we made, and my mentor used this example to show me how it's done, how it occurs, how everything is, how the entire process goes to creating a PDMS film. And these are my own samples that I created with the second test. I learned a lot from doing that one. On the third test is when we started applying the concept of adding electrical plates. So we cut a basic sheet of aluminum foil, which is similar to the size of the molding. Now this is the molding, this is the Teflon block. It's pretty much a plastic material that you can put under a lot of stress and thermal strain. And what we did was we used a sheet of aluminum and we ran it along the bottom of it. And we attached the wire to the other end so we can attach it to electrical charge or voltage supplier. So we found out that the aluminum foil peels off and is actually somewhat embedded in the center. Now our test 4, which we use with secure electrical plates. By secure electrical plates, what we mean is that we're holding it down securely on the Teflon block rather than just putting it down like we did before, where we just placed it down. I secured it with tape. It's a very simple concept, but we secured it with tape and we pretty much flattened the aluminum foil so it's really flat. Test 5 was basically my mentor testing out the same concept except with 2 electrical plates, one on the bottom and one on the top. So we wrapped the second Teflon block in aluminum foil and we used that as the electrical charge plate on the other side of the PDMS film. Now, the results of test 1 and test 2, they were created with the Teflon block, so these didn't have electrical plates yet, but they're basically clear, but it's very difficult to see through them. They're not transparent. And this is mostly due to the very tiny patterns that were created on the Teflon block when we're milling the machine. The reason why this is not something we want is because if you're placing this on an ATM or some kind of screen for blind or visually impaired people to utilize, they wouldn't be able to see past the film, and that could potentially create, I guess, communication errors or the not being able to see it properly. And so in my observations, we found out that test 1 and test 2, we basically got clear material, but they weren't very transparent because of the milling pattern footprint in the Teflon block. And it was basically mirrored onto the PDMS film when we removed it. Test 3, the aluminum foil became embedded in the middle of the pure PDMS compound. So it made it pretty impossible to remove or to even use it as electrical plates effectively. Test 4 was our successful one, and the area that was exposed to aluminum foil is very transparent, and the rough edges of the PDMS film what we had before. And test 5, we found out that it was a really good concept, except the air pockets seemed to have formed, and they weren't cleared out in the vacuum, so that's something we should be working on in the future. So in conclusion, we found out that it is pretty clear that the method that we used for test 4 that we completed is really effective and produces the satisfying results that we're looking for. And also that this method, if we use it properly, it can prevent shorts between both electrical plates due to a constant distance determined by the depth of the mold. Basically, because we're taking it down or we're securing it down pretty much flush to the bottom of the Teflon block, it'll be very unlikely to create a shortage between that and the second electrical plate. However, more experiments need to be conducted to fully determine the effectiveness of this method and also to determine the minimum achievable distance between both electrical plates. So in the future, perhaps we're looking for something that we're trying to achieve a thinner and thinner PDMS film. So that's something we should be working on in the future. And for future studies, we want to repeat test 4 as a method to generate consistent PDMS films for future experiments and applications. And we'd also like to decrease the distance between the electrical plates, like I mentioned earlier, without shorts to create thinner films. We also want to apply electrical charge and examine the particle patterns under the microscope. And basically, this is a setup and method that we use to help create and explore new options under my co-mentor's study that she used for her graduate studies. And I'd like to thank Dr. Luna Freshman from CCNY Agriculture, my co-mentors, lab workers, Laboratory for Nanoparticle Modification Assembly, Department of Chemical Engineering, CCNY, Dr. Sat, HCF, and all HCS staff members.